Welcome back to Introduction to Statistics. Today we're going to be talking about hypothesis tests for a population mean. When you perform hypothesis testing, you're using results from a sample to do some calculations and give you an idea about some characteristic of the population. Here's a reminder from the last video, the steps of hypothesis testing. Form a hypothesis, collect evidence, analyze the data. You're trying to determine the plausibility of the hypothesis. I need to introduce a couple of more terms, though. When you perform a hypothesis test, your results will be deemed statistically significant when your observed results, your calculations and everything, are unlikely if the null hypothesis is true. But just because something is statistically significant, that does not necessarily mean that it is practically significant. Something is practically significant when the difference between the null hypothesis and the alternative hypothesis is enough to cause concern or to prompt action. So let's say you estimate that it takes you 25 minutes to get to work. You think that that is the mean amount of time it takes you to get from your place of residence to work. But you're concerned that it may be taking you longer now because of road construction or something. So you perform a hypothesis test. You gather your data, you use the methods I'm going to show you, and you find out that yes, you have a statistically significant increase in the time it takes you to get to work, in the mean time it takes you to get to work. However, that statistically significant difference is 30 seconds. Is that really practically significant compared to 25 minutes? Probably not. So you have a statistically significant result that doesn't practically affect you a whole lot. On the other hand, if it normally takes you a minute and a half to commute from your bed to your computer for your 8 o'clock class currently, you will have to decide whether it is practically significant or not. It probably depends on whether your professor is a stickler for being on time and counting tardies. Here are some reminders. We're talking about hypothesis testing, so you will always have a null hypothesis, and that is always a statement of no change. You have some idea of what the mean is, and you are testing that. You're expecting that there will be no change. You will also have an alternative hypothesis, H1, where you say the mean is not that value. In this case, we're saying that our alternative hypothesis is that the mean is greater than that value. So that is a right-tailed test. And if you draw your normal curve, you're going to be looking for values, okay, that are greater than that value. How likely is that to happen? All right, then we have another case where you have the null hypothesis, once again, that the mean is equal to what it's always been equal to, or the alternative hypothesis that the mean is less than that same value, and that makes it a left-tailed test. And once again, if you draw that out on a normal curve, you're interested in something that would be very unusual. Not much of the data is down here, right? So that's a left-tailed test. All right. Then finally, we have this situation where you have the null hypothesis, once again, no change, or you have the alternative hypothesis that it's probably changed, but we're not sure whether it has increased the mean or decreased. So it's a two-tailed test. So you're looking to see if your mean occurs out here where it's very, very unlikely, okay? So that's playing fast and loose with some definitions there, but it gives you an idea of what we're doing. This is a two-tailed test. Okay, and we are going to be discussing two different ways to perform a hypothesis test. One of them is technology dependent, and one of them is not. They are called the classical approach and the p-value approach. You have seen p-values popping up when you've worked with Minitab before, and now you're going to learn what that means. Okay, here's an example from your book, Fundamentals of Statistics. Actually, this is from the 4th edition by Michael Sullivan III. In 1990, the mean height of women who were at least 20 years old was 63.7 inches. Suppose that a random sample of 45 women who are in that age range produces a mean height of 63.9 inches. It appears from your random sample here that women are getting taller. So that's going to be our alternative hypothesis. The null hypothesis will be that the mean height of women has not changed. So the population mean equals 63.7 inches. The alternative hypothesis will be that the mean is not equal to, but the mean is greater than 63.7 inches. We're not going to worry about the 63.9 inches. We're testing the null hypothesis. So we're looking for a result that is greater than 63.7 inches. So this is going to be a right-tailed test. And by the way, we just performed step 1. And that is to identify the null and alternative hypothesis. Let's make all this a little bit smaller so we have some room, because we need to perform step 2. We're going to choose a level of significance. Choose alpha. Remember what alpha is? It is the probability of making a type 1 error. Okay, so let's see, what was a type 1 error? A type 1 error was a false alarm. It was declaring someone guilty when they were not guilty. It was a smoke detector going off when there was no smoke, there was no fire. So choose your alpha. The most common level of significance that is used is 0.05 or 5%. Step 3A is to compute T null. So what is T null? That's our test value, or our test statistic. And we have a formula for that. T null is equal to the mean of our sample minus the mean of the population, the initial mean of the population, divided by the standard error of the mean. Once again, T null is our test statistic. In order to compute this statistic, we're going to have to gather all those variables. So let's see. The sample mean is here. Okay, so we have 63.9 inches. That's our sample mean, minus what was the initial mean of the population? Well, that was 63.7 inches. And we're dividing that by the standard deviation. Okay, if you notice, we have the number in the sample. That number is 45, so we have the square root of 45 down here. But we do not have a standard deviation. You cannot do this method without a standard deviation for your sample. And if you've collected this data, you're going to calculate that. Unfortunately, I did not choose my example wisely from your book. I chose one without a standard deviation. So I'm just going to have to tell you that we're going to give this a standard deviation of 2.50 inches. Okay, so down here where we're looking for a standard deviation to fit, it's going to fit right there. All right, so what is that value? That would be 0.54. That is our test value, our test statistic. But we need one more thing. We have a test statistic, but we need a critical value. So you saw that we have a t here. Yes, we're going to have to go to the t table, and we're going to be working with the level of significance when we go to that t table. So we're going to be looking in step 3b for a t sub alpha. Now this is a one-tailed test. It's a right-tailed test. So we're going to be looking for this 0.05. Also going to be looking for this with a certain number of degrees of freedom. So the number in our sample is 45, and if you remember, the degrees of freedom is always one less than that, so it's with 44 degrees of freedom. Now, this is not a common thing to do, but personally I like to do a double subscript, T sub, level of significance, and degrees of freedom. So I have it written down there, and when I go to my T table, I remember what I'm looking for. And when I go to my T table, I'm looking across the top, and I'm going to go across until I get to 0.05, and I'm going to look down that column, and then down the left-hand side, I'm going to move down the page until I get to approximately 44. You'll see on most T tables it's not there. So we take the closest thing to it, which would be 40. Moving across from 40 and down from 0.05, we get the value 1.684. So that is our critical value. Okay, let's put all this together now. All right, this is not my best illustration of a t-distribution ever, but we're going to go with it for now. This is step 4, in which you actually illustrate your results. So first, let's look at the critical region, okay? And by that, I mean this value. Okay, we are going to find 1.68. We are looking for a right-tailed test, so we're looking in the right part at 1.684, somewhere about there. And anything beyond that is the critical region. All right, so now we have to look at, and let me rewrite this so it's easier to read, our test statistic. I am going to do it in red. Is 0.54. So it is about here. There's t sub 0. Is our test statistic in the critical region? No. If it is not within the critical region, then we do not, I repeat, do not reject the null hypothesis. And now we need to state our conclusion. And there is our conclusion. There is not sufficient evidence at the 0.05 level of significance to suggest that the mean height of women 20 years old or older is increasing. Not sufficient evidence. Our test value was not within the critical region. All right, let's do this with a more abstract setup, just to get the practice doing the calculations and graphing and making comparisons. Here's example 2. The null hypothesis is that the population mean is equal to 20. And the alternative hypothesis is that the population mean is less than 20. Now, to test these, we're going to take a sample. That sample is going to have 18 individuals in the sample, but we know the population is normally distributed, so we're good to go with this method, because you either have to have 30 or more individuals in your sample, or you must be sampling from a population that is normally distributed. In addition, we are making the assumption that the number in our sample is less than or equal to 5% of the population. Next, we need to calculate our sample mean, and I'm just going to tell you that the sample mean is 18.3. Sample standard deviation is 4.3. Okay, to perform a hypothesis test using the classical method, because that's what this is, we're going to go with the routine level of significance. Alpha equals 0.05. We have about a 5% chance of rejecting the alternative hypothesis when it actually is true. So we can live with that. First, we calculate the test statistic, remembering that that is the sample mean minus the population mean divided by the error of the mean, which in turn is equal to the standard deviation divided by the square root of the number in your sample. So let's put all the numbers in there and actually do the calculation. Divide by the standard error of the mean, which is the standard deviation of the sample, divided by the square root of the number in the sample. Okay, so if we punch all that into our calculator correctly, we get negative 1.68. So that this is a left-tailed test, and our test value is negative. We still need to calculate our critical value, though. And our critical value is going to be based upon our level of significance. We're going to be looking at that across the top of the chart, and we're going to go down the chart to our degrees of freedom. So remembering that degrees of freedom is 1 less than the number in the sample, so degrees of freedom equals 17. On the chart, that critical value is 1.740. Okay, now I've drawn my t-distribution. Let's put in the critical value. So the critical value is 1.740, but this is a left-tailed test. So I have to put in a negative there. We're looking at the negative side of things, less than a certain value. So we have negative 1.740. That's going to be about right there. And it's a left-tailed test, so the critical value is in that left tail. Where is our test value, though? Our T-naught. That T-naught is at negative 1.68, not quite in the critical region. So we would say there is not sufficient evidence at the 0.05 level of significance to say that the population mean has decreased. And let's do one more example of the classical approach. Guess which one it's going to be? A two-tailed test. We're going to look at the null hypothesis. The mean of the population equals 45, and our alternative hypothesis will be that the mean does not equal 45. Two-tailed test. You will need some more information about how I went about this test. Well, I got this information because I took a sample with 40 individuals in it. The mean within my sample was 48.3, and my standard deviation was 8.5. Okay, and I'm going to do this at the same level of significance I've been using previously, so we can compare how the different tests affect things if we keep the level of significance the same. We'll work with different levels of significance later. And let's go back up here beside my number in the sample. Let's go ahead and write degrees of freedom equals 39. All right, and now it's time to compute a test statistic. Okay, remembering the formula for the test statistic, we will plug in the values that we have. The sample mean is 48.3. The mean of the population that we are expecting not to change. We're dividing by 8.5, which is itself divided by the square root of 40. And that gives us a statistic of 2.46. Now we need the critical value. It's going to be for a level of significance of 0.05, but wait a minute. This is a two-tailed test. So it's not going to be T sub alpha, it's going to be T sub alpha divided by 2, because half of that 5% is in the right tail and half is in the left. And we're going to look at degrees of freedom, 39. So specifically, this is 0.025 with degrees of freedom, 39. So we're going to go across the top until we get all the way to 0.025. Then we're going to go down to degrees of freedom, 39. And when I go across that row and down that column, I get 2.023. So I have my test value and I have my critical value. Now this is a two-tailed test, so I actually have plus or minus that value. So let's put it on a t-distribution. Okay, the critical values are negative 2.02, so that's close here, very close. And beyond, same thing over here. And what is our test value? Our test value is 2.46. So 2.46, that's where that goes. There's one of those. Is there sufficient evidence? Is that value in the critical region? Oh, yes. So yes, this time we have significance. There is sufficient evidence at the 0.05 level of significance to say that the population mean has changed. All right, I'm going to leave it there for this video. I'm not going to go into the P approach as I'd originally planned. I think a lot of practice with the classical approach is not a bad thing. So we'll move on to other approaches in upcoming videos.